this lecture series will be delivered by Professor Athanase Papadopoulos. So I think there's no need of introduction.
And then I want to talk about my second example. This is the Funk metric. On convex, well, this is now defined on convex bodies. The main reference for this kind of metrics is there are papers by Buseman. And I'm happy because our Egyptian colleague here asked me whether I will talk about the Buseman, and I like very much what Buseman wrote. This is the kind of geometry which is based on simple principles. You know, you don't have to know a lot of things. You don't have to. I mean, it's not the kind of theorems where you take theorem A and theorem B and you mix them and you find theorem C. These are theorems which you prove just by hand, by geometric constructions. This is why I like very much this kind of geometry. So this is convex bodies in, yes, convex bodies in Rn. I assume that you know what is a convex body. If not, I will just give this definition. So you have, let's think that you have, and let's say that you have, well, an open subset omega in Rn, which we assume to be R2 here, such that for any 2 points, x and y, the Euclidean geodesic, the Euclidean straight line joining them is contained in this subset. I will talk a little bit about convexity later, and we have our colleague Ismesiev who will talk more about convex sets. I mean, this convexity is something very, very important. You will see later why. But for the time being, we just need this definition of a convex set. And then I will define this Funk distance, where the distance, let's call it f, between x and y is defined in the following manner. You take the straight line between x and y, which you know is in your subset. You look at the first, well, you look at the first and the last point where it hits the boundary of omega. You call it B. So the straight line starting at x, passing through y, because of the convexity. So because just of this property which I said, there's only 1 point. There's only 1 point of intersection. That is, my set cannot be like that. If it were like that, then it would be 1, 2, 3 points. But because of convexity, there's only 1 point of intersection. And you define this as the Euclidean distance, well, between x and b divided by the Euclidean distance between y and b. And you find something which is a metric in the sense I explained this morning. It doesn't, I mean, it satisfies all the properties except the symmetry, because you see, suppose that x is here, and you can see immediately that well, the distance between x and y, which is this divided by this, there's no reason that it's the distance between y and x, which is this divided by this, which is close to 1, you see. The distance from y to x is close to 1, whereas the distance from x to y, yes, you are right. Thank you. I have to take the logarithm so that if this is equal to 1, then the distance is 0. Okay, because when the so f of x equals 0. This is I take this definition where when x is different from y, and I set f of x is equal to 0, and because of the logarithm here, by this would give you a continuous distance, and it will be equal to 0 if and only if s is equal to y. X is equal to y. So what do we do with this? We have a definition now. Let me also give another exercise to prove the triangle inequality. So this morning I gave the exercise for the other metric, and then Shreyas, where are you? He just told me that he proved it. Did anybody else prove this triangle inequality for this morning? Okay, so this should be a little bit more tricky to prove. It's not obvious, in fact. It's not obvious because you see the distance between you want to show that the distance between x and y is less than the distance between x and z plus the distance between z and y. So you take another point here, z, and then to find the distance between x and z, you have to take this point here, c, and the distance between z and y, you have to consider this point c and take this point d and take this ratio. So you have to deal with these six points at the same time. There's a geometric. There is a geometric way of proving the triangle inequality, which is not obvious, but it is true. Okay, this is one thing. Let me just mention to you that before we continue that this is what I called SF of xy. That is the symmetrization 1/2 f of xy plus f of yx. This is the Hilbert. This is well-known metric. The Funk metric is not so much known, but this is the Hilbert metric. This is the Hilbert metric on convex sets where you take 2 points, x and y, and you define the Hilbert distance h of xy. This is h of xy as half. So this point is A, this point is B, and this is half of, well, x minus b, y minus b, y minus a, x minus a, and there's something here. There's a logarithm. There's a logarithm here. So this definition is the same. Is the one I gave here, and this what you get here inside the parenthesis is the denoted like this, and this is called the cross ratio. The cross ratio of the 4 points A, X, Y, B, which is very interesting for several reasons. One of the reasons being that the cross ratio of these 4 points is invariant by projective transformations. So this makes this Hilbert metric, well, let's call it a projective metric. The meaning of projective, there are several meanings to projective metric, but now everything you need to know, and which is this projective invariance of the cross ratio, the projective invariance of the cross ratio, means that if you apply to this set omega projective transformation of the plane, which preserves it, then this transformation is distance preserving. It's distance preserving just because this, I mean, it's a theorem that this cross ratio is preserved by projective transformations. Let me write here. Let me write here. In fact, what this projective property means. It just means the following. It means that if you have 4 lines like this intersecting at a point, if I take a line intersecting them which at 4 points, A, X, Y, B, and another line here which intersects them at A prime, X prime, Y prime, B prime, then what I call this, the thing which I just wrote, which is A, X, Y, B, is equal to the cross ratio of A prime, X prime, Y prime, B prime. This is the projectivity. This is the property of the cross ratio, which is the invariance by this kind of map, which is called also a perspectivity. You know, it's like I'm doing perspective drawing from this center here. So AX. So this quantity is invariant. So this is every time you have a transformation like this, which is preserved, then the cross ratio is preserved. So anyway, so this is one. I mean, because sometimes, because you can ask, okay, why do we study this metric? One reason is that what I just said, the Funk metric is something like half of the Hilbert metric. Okay, so many people study the Hilbert metric. You could study the half of the Hilbert metric, which is, I think, as much interesting. And one of the reasons why the Hilbert metric is interesting, so Hilbert metric, which I just defined, and which is the symmetrization of this Funk metric. The Hilbert metric is, in fact, if you restrict it to the, well, we talked about the upper half plane model of hyperbolic geometry. I could say the same thing, in fact, for the upper half plane, but I don't want, since I drew this, an open convex subset, let's say bounded, or relatively compact. It could be also for non-bounded, but let's not complicate the thing. So in particular, I can take the disk, Hilbert metric of the disk, any disk, the unit disk if you prefer, in the plane or in n-dimensional Euclidean space. So this is a model of hyperbolic geometry. A model of hyperbolic geometry, which is called the for the reason I just explained. This is called the projective model. So hyperbolic geometry is defined. You see, hyperbolic geometry as a non-Euclidean geometry is defined without any use of any model. I mean, you just take the Euclidean geometry, you replace the axiom, the parallel axiom, by its negation. You say that the parallel axiom is not satisfied. This is all what you need, and you get a geometry which is the well-known hyperbolic geometry which you use today. And many theorems of hyperbolic geometry, you can prove them without any model, in fact, just by thinking, just by imagining. I mean, just no need to have formulas for the distance, for the infinitesimal length element, and so on. But sometimes models are useful, and in particular this model here, where you have x and y, and the distance between them is this cross ratio of these 4 points. It's useful because it includes the study of hyperbolic geometry as a special case of projective geometry, because the isometries of this metric are I mean, the motions in this space are just the projective motions of the plane which preserve the disk, and you are doing projective geometry. So this is one of the reasons of this, that you study this metric. Now, so this was a little bit of advertisement of why is the Funk metric is interesting, but it's interesting in its own right also. It's interesting in its own right. It's its own right because you can prove nice geometrical results on this, and I want to tell you the kind of results which you can prove. One of them, let me prove a result about geodesics. So we asked the question this morning, what are the geodesics of this semi-weak quasi-hyperbolic metric? Now I ask the same question of geodesics for this metric here, and I say that the Euclidean lines are geodesics. And if you think about the proof, then you will find it immediately. You see, if you remember how do we define geodesics, then you know what to prove. This is a Euclidean line between 2 points x and y, and you want to prove that it is geodesic. So you want to prove that if I take 3 points here and I compute their distance, then the triangle inequality is an equality, right? So in fact, let's imagine that this is my line and that x and y are 2 of my points, and then z is between them. When I compute the distance from x to y, I have to extend here until this point b, and then it is the logarithm of this distance divided by the logarithm of this distance. The distance between x and z, it's the logarithm of this distance divided by the logarithm of this, divided by this distance, and the distance from z to y is the logarithm of this distance divided by this distance, right? And then you use the property that the logarithm of the product is the sum of the logarithms, and you get your triangle equality. Okay? And you can, so you can do this for any 3 points here inside, VWT and so on and so on. So these straight lines are geodesics. Now I want to say something about another question which I mentioned this morning, and this is about the uniqueness of geodesics joining 2 points. So I will make the same reasoning now, and I will take this example here where there is a straight line, a segment, a Euclidean segment in the boundary of omega. This is omega. So this is an example where omega is not strictly convex. Not strictly convex means that the boundary contains a Euclidean segment. Okay? And now I take again here, I want to take 3 points, x, let's say, y, and z, like this. And then I take this broken segment between them from x to z and from z to y. And I want to say that this broken segment is also a geodesic for my metric. Okay? So I compute distances. Let me first show that the triangle equality is valid for these 3 points x, z, and y. And then I will I will not do it, but it will be the same for any 3 points here, here, or here, any 3 points on this broken line. So the thing is that because of the existence of this straight line, I can make the following picture here. I take the perpendiculars, the three perpendiculars. I call this, let's call it the z prime, x prime, y prime. Then this is the distance from x to z, which is equal to the distance from x to z, which is equal to the logarithm of this distance divided by this distance, also equal to the logarithm of this distance divided by this distance, right? Because of the similarity of the triangles, right? And the distance from z to y, which is equal to the logarithm of this divided by this, is also equal to the logarithm of this divided by this, and so on for the distance between x and z. It is the same. The distance from x to y, which is this, the logarithm of this divided by this, is also equal to the logarithm of this divided by this. And because of cancellations, I have the Funke distance between x and z plus the Funke distance between z and y is equal to the Funke distance between x and y. Okay? So in fact, each time I have a convex set with some very small segment here, I can make all this picture here for 3 points that are very, very close to my segment. I mean, I will manage to make this picture. So each time omega is not strictly convex, then there are many geodesics in fact, because I did this, but I could do also this. With the same reasoning, I would do also this, I would do also this, I would do something probably from the other side, like this. There are many geodesics between x and y. And you see, the converse is also true, because you know that in Euclidean geometry, you see this kind of triangle inequality is an equality if and only if there is a straight line. If and only if we are on a straight line. So the statement is this one. Let me make it a proposition. Omega is uniquely geodesic. That is, for any 2 points, there is one and only one geodesic, if and only if omega is strictly convex. Okay? You understand this? What about the Hilbert metric? In fact, the Hilbert metric, it's a little bit more complicated, because if you think again about this proof, you see, so let me, so this is x, this is y, and then I have z here. I was able to make this reasoning because of this, the existence of this segment here. Now, you see the Hilbert metric is a symmetrization, right? You remember, I just wrote it. It's a symmetrization of this one. So I have to be able to make this reasoning on the other side also, right? So I have to be able to make, so, and if I want to make the same reasoning on the other side, I have to have here a segment of a straight line here on this side. So there is, and if you think about it, you will immediately end up with this proposition for the Hilbert metric that let's put it here. Proposition. So H, the Hilbert metric, is uniquely geodesic if and only if, and now you want to formulate something in a reasonable manner, if and only if there exists, let's reason in the plane. In higher dimensions, it's a little bit more involved, but let's reason in the plane. There exists, well, if and only if what? Yes, in fact, if and only if there exist two segments, two Euclidean segments in boundary of omega, two non-trivial Euclidean segments that is non-reduced to a point, okay? And which are not parallel. I mean, which are not, yeah, we can put which are not parallel. I mean, just, this segment, this Euclidean segment here, this Euclidean segment, which are disjoint. I don't know how to formulate this in an economical manner, which are disjoint and not parallel. This should be correct. So here, if I take this one and this one, then they are disjoint, but they are parallel. In fact, they are more than parallel. I could replace parallel as lying on the on the same straight line. But if I take this one and this one, then it's not. No, yes, I'm not satisfied with this. Which are not parallel, which are not. You see, which are not collinear. In fact, I just want to exclude this and this, but they can be parallel, of course. Okay, which are not collinear. And in dimension n, it should be, the result should be that H is uniquely geodesic if and only if there exist two non-trivial segments which are disjoint, and disjoint and in the same plane, coplanar. Disjoint and coplanar. Disjoint and coplanar, so that I can make this picture. Let me. No, coplanar means in the same two-dimensional plane. That is, there is such a plane which cuts such a two-dimensional plane which cuts my convex body. Let me mention that. Yes. Yes. Yes.
So if we look for y and do the same thing
Here.
Yeah.
Yes.
So
I have to be able to do it on the other side. Yes.
right. So that result like it is uniquely geodesic if and only if omega is strictly convex. So
For the Funk metric, you mean? For this one? This one, yes. Yes. For the Funk, not for the Hilbert.
Yeah, for the Funk metric.
Yes.
Yeah. So by strictly convex, so what if you have just this one side like a straight line and otherwise
This is not strictly convex.
it is not
No.
strictly convex?
No. Strictly convex means that it does not contain a segment of a straight line. That the boundary does not contain a segment of a straight line. This is the definition of strictly convex.
So if we have just one straight line, a boundary has just one
Yes.
straight line, and otherwise it's like
Yes.
so it is not a strictly
It is not strictly convex.
here if we go from y to x and so on the other side we won't be able to make this
Yes, right.
inequality.
Yes, yes, inequality, yes.
That's why, okay, that's why it is not.
Yes, exactly. Yes, okay. Okay, let me make just one remark. So here you have, I told you, you have x and y, because of the existence of this. We drew a lot of geodesics. But you see, the geodesics I drew are just concatenation of two segments, but there are many more. In fact, you see, for instance, if I take a smooth line like this, you see, I can approximate it. You know that I can approximate it by, I can make it to be the limit of polygonal segments, and apply to these polygonal segments the same reasoning. Triangle inequality will become an equality, and this equality will pass to the limit. So I will also have smooth geodesics between these points, not only polygonal lines. Okay, so there will be a lot of geodesics. This metric will have a lot of geodesics, and you can, I think, if you are interested in this kind of thing, you can take for instance, a triangle. Take a triangle, for instance, this one, or if you prefer symmetry, you can take an equilateral triangle, and try to think about something like this. Well, I want to take two arbitrary points in this triangle and describe all the geodesics between these 2 points. This is a very good exercise. I think nobody did this until now. You want to study you want to say something interesting on on the union of all geodesics joining 2 arbitrary points. So I think there will be cases here, depending on, you see, I don't know, this equilateral triangle has a lot of symmetry, so whether the points are all in the same region or not, or something. I mean, I didn't think about this more than 5 seconds, but I think it's interesting if you have time to think about this. Describe all the geodesics for special cases. In the case of, okay, the same question may be asked for the Hilbert metric. The same question could be asked for the Hilbert metric. The Hilbert metric, say, of this triangle. We know that it is not uniquely geodesic because of this proposition here. And I ask you to describe all the geodesics between 2 arbitrary points to make an algorithm that will draw the region. You see, I think that if you take 2 arbitrary points here, x and y, depending on their position, you know, in the general case it will be difficult, but here in special case, depending on their position, then you will have something like that. You see, you will be able to draw a region like this, which is the union of all these geodesics. So this is one thing you can do. Another thing which I mentioned this morning. Another thing which I mentioned this morning, instead of geodesics, another thing is that you can study what I call circles or spheres if you are in higher dimensions. And this, let me start by an example. So this is, again, a simple example. The example of a triangle. And I take a point here. I take a point in this triangle. Let's call it x. And what is a circle? So there is, as you remember from this morning, there are the positive, the right circles, and the negative or the left circles. S plus of xr, this is the set of y such that f of xy is equal to r. Okay, so I start like this. I want to start like this. I take a line from this vertex passing through x, and here I take a point y. You see the distance from x to y for y varying on this line varies from 0 to infinity, right? From the definition, the distance from x to x is 0, right? And the distance between x from x to a point here, y here, well, this is this distance here divided by this very, very small distance, so the ratio becomes more and more, and it becomes infinite, right? So I can find here on this straight line, I can find a point y, which I draw here, belonging to this sphere, this positive sphere. Okay. And now I notice the following. I notice that from the point y, if I take a parallel to this edge of my triangle, then for any point on this parallel, so here a point, say y prime, let's call it z instead of y prime, it's clearer. For the point z, you see that this, sorry, this is from the distance from x to z, the distance from x to z is this, the logarithm of this divided by this, right? And because of parallelism, it is equal to the logarithm of this divided by this, right? Because I have similar triangles, okay? So in fact, the result is that all the points which are on this line belong to this circle. So I can continue. I can continue indefinitely. See from here, here, and then I must stop. I must stop here. Sorry, it's not this, it is this. I must stop here. My reasoning stops here, and it stops here. It stops here, because if I continue now, then I go outside the triangle, I cannot continue. So what I know is that this piece belongs to my circle, right? This piece belongs to my circle. And then when I stop here, I can continue in the other, parallel to the other side, and I do the same reasoning. You know, this divided by this is equal to this divided by this, and so on. I continue, and here now I am stuck here at this point. I cannot continue after this point because I arrive to this. And then I must take the other parallel. And because of the geometry, because of what I'm trying to prove, I know that I showed, in fact, I showed you an intermediate theorem, which is that this line must close, right? Which I mean, it's clear from the geometry, but it's not. It's also a consequence of my construction. I proved a new theorem that this line must be closed here. You remember I asked you this morning for general sets, when you have this kind of question, you want to know whether the circles are compact or not, whether they are connected. You have examples, in fact, some other formulas of other geometries where this is not connected. But the important thing is that what I proved is that this sphere, in fact, this sphere is a triangle which is similar to the big triangle, right? It is similar to the big triangle, and yeah, I am happy because the big triangle here, as I told you, is something which is at infinity of my space. A point here, if I am in this space at this point, I cannot see the infinity. I cannot see the infinity. I just see what is around me. I see what is around me. And in fact, by drawing a sphere around me, by drawing a circle around me, I know the shape of my infinity. You see? I know the shape of my infinity just by drawing. I can draw a very, very small circle here, a very small circle by taking R. Well, I have a picture of my infinity. And in fact, it's a theorem. In fact, a little bit. It's not complicated, but it's a little bit more work. You have the following proposition that the right spheres are, I use the word similar. In fact, there's a technical word which is I think homothetic is also possible. Homothetic to boundary of omega. There is a homothethy. There is a homothethy of which takes this circle, this small circle, to the boundary of my space. The question for the question is what about, and this is general for any Func metric. For any Func metric. I did it for triangles. I did it, but in fact, you can do the same reasoning for any shape at infinity, or if you don't like, if you prefer to, I mean, if you prove such a thing only for polygons, then you're done, because you can approximate from inside any kind of convex. This is a property of convexity which was known since the Greeks. You know, you can approximate them by inscribed polygons. In the work of Archimedes, there are such theorems. Approximation of curves by convex polygons. This is how he computes the lengths of curves. Anyway, so for any Func metric you have this, but the question is, what about the Hilbert metric? So those who want can think about this. What do you mean? Yes, the right. This is the right. Yes, you're right. Yes, the plus. Yes, the right spheres. For the left spheres, you can think a little bit about it. You will see that the left sphere in this metric are not compact.
I was thinking something in terms of right triangle.
Yes, I understand. No, maybe the right is not, positive. I will call it positive instead of right. For some reason, I think Boseman calls them right. So there is no, or at least I don't know about, any statement like this for the Hilbert metric. There's a paper by a student of Boseman, and I think he is Indian. Boseman has had an Indian student, and the paper is in this paper he takes a triangle. And he constructs, he takes a point in that triangle, and he constructs a sphere. And the sphere inside the triangle, in fact, is a hexagon. The sphere is a hexagon. And the title of the paper is something like a triangular world with hexagonal circles or hexagonal spheres, something like that. And this is the only explicit construction of a right sphere for the Hilbert metric. Of course, there's also the construction of the spheres in the Hilbert metric in this very well-known space where your convex set is a disk, and where the spheres, as I said this, in fact, this morning for the upper half-plane model of hyperbolic space, but it's also a theorem. It's a result that in the you see, now I'm talking about the Hilbert metric, not the Poincaré metric, the Hilbert metric of this, where the distance between 2 points is given by this cross ratio. So it's also a theorem that the circles are Euclidean circles. It's true for the Poincaré model, and it's true for the Hilbert model. So apart from this case and this case, for the Hilbert metric, I don't know any explicit construction. I would imagine that that if you have n polygon here, but I never tried to prove it, and I don't know if it's true. I mean, it's just conjecture based on just on this similar. On the construction here. This would say, I'm not sure it's correct. I mean, the obvious conjecture is that you will have a polygon of double the number of sides, but you have to be careful. In fact, I'm not sure. Maybe you have to consider. You have to subdivide here and consider regions and so on, and it depends on the region. I don't know. I mean, I don't know. If somebody wants, he can start with the case of a square, in fact. Okay, so these are a couple of things on the Funk metric, the Hilbert metric. Of course, there's the questions about the Gromov hyperbolicity, which Besson and Courtois will talk about. The Gromov hyperbolicity. This is the behavior of large-scale triangles, and there are several things to say, and there are results where Gromov hyperbolic if and only if. Well, it has to do with the smoothness of the boundary, the fact that it is true or not. There are several works on this. So I said that this all this started with work of Busemann, and then it was revived. The subject was revived in the year around the year 2000 by several people, especially in France. And it's quite a good subject because, as you see, I mean, you don't need any sophisticated mathematics to work on this. And this is the kind of mathematics which I like to work in. Okay, so this brings me to something which I want to talk about. That is the Finsler structure, and I want to talk about it here at this point. So what is a Finsler? So there are different points of view on Finsler geometry, and you can everyone has his own capabilities, his own sensibilities, own imagination, and there's an analytic point of view with, it's not analytic, it's a point of view with differential geometry, which I don't want to talk about. I want to tell you what is a Finsler manifold from this point of view. I don't want to talk about the other point of view because I'm not capable of doing it. I'm only capable of doing things which are in the style which I showed you. So what is a Finsler manifold? So you have a manifold which I don't want to complicate things, and my manifold here is just my omega. If you like to work with subsets of Rn, you can just imagine you have a subset of Rn, let's say a convex open set of maximum dimension Rn. Although for this definition I don't need anything. I need convexity, but not for the definition of the open set. You have an open set in Rn, so and equipped. Well, at each tangent, I even don't want to talk about tangent space. Equipped at each point. With a convex, say a convex open set containing containing this point. So a Finsler structure is just a family of convex sets parameterized by some manifold or by a subset of Rn. So here I have again my omega convex set. So at each point I have a convex set, 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 I have a convex set. And let's say that it's not really necessary. I will tell you what is necessary. I will tell you what is necessary, but let's put it here. Varying continuously with the point, and you will see why it's not really necessary. You when you see what I want to do with this, and then these convex sets. Now this is the definition, and now what you imagine. Each such convex set, you want to imagine it as a unit ball. Is the unit ball of some norm, but remember that we are in a non-symmetric setting. Okay, so this norm, I mean, it's a norm except that it's not necessarily symmetric. You see, if suppose that this is my point, this is the convex set. You see, this convex set is not symmetric around this. So this convex set will tell you that this vector is a unit vector. 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 It tells you this convex set gives you all the I'm using something on convex sets. You know that the boundary of a convex set is always a sphere. This is a topology. This is a topology. So you have a unit sphere also. And then this unit sphere gives you the set of all vectors of unit norm, and then you can measure the length of any vector, in fact, whether it is unit norm or not, because you know the length of this vector here. So this vector is lambda times this vector. So you will multiply. You will find the length of this vector. So this is how this convex set at this point gives you a norm which satisfies all the properties of the norm except the symmetry property, which we don't want because we are not interested in symmetric metrics. And this is the Finsler structure, and with such a structure you can calculate, you can compute lengths of curves, lengths of C1 or lengths of C1 or piecewise C1 curves, because you take a curve in this space, a differentiable curve. There's a tangent vector at each point. I said piecewise C1. I mean, you consider only the places where it's C1, and then you because of this field of convex sets. At each point you have a convex set. You can compute at each point the length of the tangent vector. You integrate, and then you find something which is the length of your curve. Okay. When I said before that the continuous variation of this field of convex set with respect to the point is just because I want to be able to compute this integral. But to compute the integral, you know that you can integrate things which are discontinuous, you know, and then just measurable. I think just measurable or upper semi-continuous, something like that, is sufficient. So for the Finsler structure, I even don't need any continuity. I just can deal with upper semi-continuous to compute the length. And then once you can compute the length of C1 or piecewise C1 curves, you can define a distance on your manifold or on your open set in Rn by saying that the distance between 2 points is just the infimum of the length of the curves joining them. And because of this Finsler structure, I know how to compute the length of curves, and the conclusion is that it gives me a distance function. It gives me a distance function. I can say what is the distance, and because of the way I defined it, you know, the infimum of the length of curves joining them, the triangle inequality is automatically satisfied, because if I have 3 points, then the curve joining this concatenated with the curve joining this to this, then is also a curve joining this to this, and so on. So everything is fine. So this is a very weak form of a Finsler structure, which defines for you a distance function. And now the question is, I take a metric on an open set or a manifold. I think everybody here knows what is a manifold, but I want to stay very basic. Let's take an open set on Rn. I take a metric defined by some definition, like the metric of this morning, or like this Funk metric, or like the Hilbert metric, and then I asked, is it a Finsler metric? So, for instance, the Funk metric, log of x minus b, y minus b. Does this come from a procedure like this? Is the metric defined by this formula? Is the metric defined by this formula a Finsler metric? And the question is interesting for the metric we saw this morning. I don't know the answer. In fact, I would suppose no. I don't have any supposition. No, I have no supposition. So you can try to answer the question for the metric I gave you this morning. There are a lot of metrics which I don't know whether they are Finsler or not. In fact, I don't know, and the metric of this morning has a nice formula which you can, if you want to work on it. But there are metrics, for instance, on a little bit more sophisticated spaces, which I will talk about at the end, metrics on Teichmüller space, you know, which are interesting, and on which I spent years and years, and I still don't know whether they are Finsler or not. I would like to know whether they are Finsler or not, but I don't know. There are open questions there, real open questions. This question about this morning, I don't know also, but I never thought about this. But for the Funk metric, the answer is yes, is Finsler, and in fact, there's something interesting here, is that the Funk distance, in fact, the Funk geometry, let's call it Funk geometry. Funk geometry is, in fact, something tautological, something we call the tautological Finsler geometry. This term I introduced with my co-author. This is Mark Troyanov, with whom I wrote several papers on the Funk metric and also on the Hilbert metric. So this is from this point of view. So this is we were happy to find this word, you know, and I want to explain to you why it is tautological. For the tautological means, this is a Greek word. It means I mean, you know this word, the tautology. So it means that it's its own. I mean, okay, you will understand why. So I have a convex set on which I have defined the Funk distance. This is my convex set omega, and in fact, this is a Finsler metric, where at each point the convex set is the convex set omega itself. This is why it's tautological. So at this point, the convex set is the convex set which measures which gives me the unit ball at this point is this convex set centered at this point. The convex set which is the unit ball is this convex set centered at this point. They are all different. Because the center is different. You see, if I take the Funk metric of the unit disk, then it's only at the center of the disk that this convex set is symmetric. At the other points, at this point here, this is my convex set, and it's not symmetric. It's not symmetric at this point. This is a length 1, and this is here a length 1 vector. So they are all different. The metric is not symmetric it's always non-symmetric. So it varies from point to point, but it stays the same. It is varying, but it's the same, right? Okay. So this is the Funk geometry of the. This is the Finsler geometry of the Funk geometry, and now the question is for the Hilbert. The question is for the Hilbert. So I told you that the Hilbert metric, the Hilbert geometry of this convex set here, the Hilbert geometry, the Hilbert distance is a symmetrization of the Funk distance, right? It is you take the half of the sum, you take the arithmetic mean of the distance from x to y and the distance from y to x. So the question now is, okay, so in that paper with Troyanov, in fact, or in another paper anyway, in a paper with Troyanov, with this definition I gave you of the Finsler geometry, you have we have a theorem saying that if you have a Finsler metric, f, then its symmetrization, you see, its symmetrization S of f is automatically Finsler, is also Finsler, and we have a method for describing the unit ball at each point of the symmetrization from the unit ball of the initial metric. In particular, I want to tell you the symmetrization for this case of the Hilbert. Let me mention that for the other symmetrization, the maximum symmetrization, I don't know if this theorem is true. I mean, I think it's true, but I don't know how to prove it. I don't know. In other ways, I take in other way I take Finsler metric, which is not symmetric, and general Finsler metric, and I consider its max symmetrization. The question is this again a Finsler metric? And the answer is, I don't know the answer. It's a question where we thought about it for a few months, and we don't know the answer. Okay? But for this symmetrization, the arithmetic symmetrization, the answer is yes. The answer is yes, and the result is here is another thing. So it is that the answer is yes. I just say it. I don't need to write it. Okay, let me write it. The arithmetic symmetrization of a Finsler metric is Finsler plus the following. Well, let's make it a statement. And at each point, the, well, let's call it the unit ball, you know that to describe a Finsler structure, you must describe a convex set at each point, which is the unit ball of your metric. So at each point, the unit ball of the symmetrization, is, it must be a symmetric unit ball. It must be a symmetric convex set, right? It must be symmetric with respect to the origin. But in fact, there are infinitely many ways to symmetrize a convex set. This is a whole chapter in convexity. You have a convex set like this one, you see, which is non-symmetric, say like this. It has a part of the boundary which is polygonal. And what is the natural way? What is a symmetrization? So there are several symmetrizations. But here there is one which is called the symmetrization is the harmonic symmetrization of the original unit ball. And I will explain you what is the harmonic. You see, the professor who presented me this morning, he said that I am interested in music. It is true. In fact, he found this on my web page. But this harmonic thing doesn't have anything to do with music. I will explain to you what it is. So what is the harmonic symmetrization? This also goes to very an ancient thing. It goes to the Greeks, and in fact, the harmonic they use the harmonic because it was used in music. In fact, this kind of mean. You see, suppose this is my convex set, and this is my origin. It's a convex set containing the origin, and I want to define a new convex set which is symmetric with respect to this point. So I take this I take this. So I take a line. We are in, well, even in Rn it's the same thing. I take a line passing through this point. Because of convexity, this line intersects, this Euclidean line intersects my convex set into a segment, connected part of this three line. It's a segment, and this point belongs to this segment, and it cuts the segments into two subsegments. Let's call them S and T. And now the harmonic mean, in fact, I'm sure many of you have already encountered this, but maybe this is the moment to see that it's useful in Finsler geometry. The harmonic mean is M. M is the harmonic mean. Harmonic mean of S and T. I'm not sure. I think it's 1 over M is, I think it's 1/2. I'm not sure about the 1/2. 1 over S plus 1 over T. Anybody knows this? Anybody can confirm? Yes, so it's this. Yes, okay, thank you. I take the harmonic mean and I replace this segment here. I replace this segment here by another segment which may be like this, the blue segment, which is symmetric around the origin and whose length here is M and M. Symmetric around the origin and where the radius here, the radius is M. And I do this for any one of these segments here, for any one of these segments. The union of all these segments, this is a proposition in fact, the union of all these segments is a new convex set, which we harmonic symmetrization of the initial convex set is the one you need to describe the arithmetic symmetrization. So in other words, the Finsler structure of the Hilbert metric is, well, the harmonic symmetrization of the tautological Finsler structure. And when you know this, then it should be easier. You see, I drew an arbitrary convex set, and I asked you show me the Finsler structure. Then now you know it. It's immediate. I mean, it's its own. The Finsler structure at this point is just this convex set centered at this point, and so on and so on. And now I asked you show me the Finsler structure of the Hilbert metric, and now we have a way to do this, because at each point, well, it's a little bit complicated, but I think a computer can do it if you know how to do this. Or you can also do it by thinking for special cases. What is the Finsler structure at each point of the Hilbert metric of a triangle? You remember before I asked a similar question, but it's not the same question. I asked questions about spheres and circles, you know, but at each point, now here it's different. It's not the convex. In fact, I even the spheres will be convex for both metrics. Here it's different. A different question. It's about this. It's about the Finsler structure. It's the infinitesimal. It's not the spheres. It's not the spheres of finite radius. It's infinitesimal spheres. These Finsler convex sets associated with Finsler structures are the infinitesimal spheres. So we have at least a way. We have at least a manner to describe this Finsler structure of the Hilbert metric. So I think I will stop because is it okay if I stop now?
Yeah.